All right, welcome to section 6D. Again, I haven't prefaced this for a while. Before you go through the video lecture, you should be reading this section on your own, making little comments in the side margins and highlighting, making questions and writing them down so that you're prepared for the video lecture. All right, let's go through it. Roman numeral 1, statistical significance. Let's just suppose that we're checking the fairness of a coin that's being flipped. We do 100 flips and we get 52 heads and 48 tails. Uh-oh, we know that it should be 50-50. So are we going to conclude that this coin is unfair? To have 52 heads and 48 tails, it should be 50-50, right? No. We should expect 50-50, but a little deviation is bound to happen. And therefore, we're not going to say that this coin is unfair or loaded somehow. If we were to have gotten 20 heads and 80 tails, however, this could be an odd chance or the coin is unfair. Our definition of when the difference between what is observed versus what is expected is greater than chance, then it's considered statistically significant. Here's a couple of examples about determining if our results are statistically significant. A Major League Baseball team has a worst win-loss record, and this team defeats the team with the best win-loss record. Statistically significant or not? In our case, not statistically significant. Even the worst teams at some point, in the major leagues at least, will win some of the time. Let's move to the next example. Global average temperature. 5 of the years between 1990 and 1999 were the hottest years in the 20th century. The 20th century is how many years? Well, a century is 100. So 5 of these years out of these 100 years were the hottest. So 5 divided by those 100 gives me 1 out of 20. And to have 5 of the hottest years in only that 10-year span is moderate to pretty statistically significant. The next one, sample population. A poll of 1,000 people stated at 51% supported President Bush when he was in office. A week later, another poll of 1,000 people, and by the way, this is all made up information, so you can change this for whatever you would like. So let's suppose a week later, another poll of 1,000 people were polled and only 49 supported. This is touted all over the media, and therefore his opinion, America's opinion, is dropping, correct? From 51% to 49%. So should we go ahead and conclude that? I know there's a lot of studies and media results that would say so, but remember, a poll isn't an exact match of the population. It's from a sample, and the whole population would be a census, and we would poll everybody. And so from one sample to another sample, we should expect a little bit of change, and going from 51% to 49% really isn't statistically significant. However, if we saw a 70% to a 30% drop, then I think we could go ahead and state definitively that it was statistically significant. Even if it wasn't the exact population proportion, it's showing that there was some decrease. Let's move to the next one, D. Some experiments. A double-blind experiment of an herbal formula. 100 random people take this herbal formula, and 100 random people take the placebo for this double-blind experiment. So we know there's no bias. That's good. Out of these 100 people, 30% of the treatment group, those who took the herbal formula, got a cold. The control group, 32%, get a cold. Is this statistically significant or not? Well, only 2%. That seems pretty likely. So I would state not statistically significant. Quantifying statistically significant for the herbal experiment, would 22% of the treatment group and 34% of the control group be statistically significant? Well, it's a little bit more dramatic, a percent change. We really need a hard and fast rule to decide if it's statistically significant or not. What we've done from A to D is just use some critical thinking skills. we need to move to this hard and fast rule to decide if it is actually statistically significant or not. So that moves us to significance levels. If the probability of an observed difference occurring by chance is 1 in 20 or the decimal of 0.05 or less, the difference is statistically significant at the 0.05 level. If the probability of this observed is occurring 1 in 100 or 0.01 or even less, then the difference is statistically significant and at the 0.01 level. If you end up with something in much larger quantities, in more than 1 out of 20, then it is not statistically significant to our hard and fast rule. So let's go back to our 22% versus 34%. After some calculating, and you don't have to do the calculating here, this is a chi-squared test that some of you might get into if you move into statistics, and so it's just beyond our class, and we'll calculate it for you. It gives us a 0.05 level, and if these same results actually happened by chance versus just, or in our treatment group versus the control group. So 1 out of 20 experiments would give the exact same 22% to 34% chance. It's a rather small chance, so it's more likely that this treatment is actually working. But it isn't conclusive because 1 out of 20 is not a huge significance. The 1 out of 100 is a better statistically significant level. Let's move to our next example of the polio vaccine. 400,000 children were chosen for this experiment. Half of them were given the vaccine and half were given the placebo, so 200,000 children each. Out of the 200,000 that were given the vaccine, 33% or 33 contracted polio. Out of the 200,000 which didn't receive any sort of vaccine, but just the placebo, 115 contracted polio. Now remember, we don't have to calculate the significance level. That will just be given to you. So after some calculating, we get that this is less than 0.01 level. The probability of getting these exact same results just by chance in another experiment is less than 1 in 100. I know it says less than 0.01. This is less than 1 in 100. That means that this is statistically significant, and therefore we can conclude that the vaccine did work. And it did work, and we have abolished polio. Roman numeral 2, margin of error and confidence intervals. A poll was conducted and 74% of Americans stated that they supported Obama with a margin of error of 3%. The margin of error defines our interval where the population proportion is likely to fall. Okay, so now we have to think back about what population proportion means. The population proportion means the entire population. And what we did is only a poll. And the poll was only a sample of the Americans, where the population is the entirety of America. So we need to give ourselves a little bit of wiggle room. This 3 points is our margin of error that says if I add and subtract this, it gives me kind of an area of where the entire population is likely to fall. And so what I would do is add and subtract it to my 74, which gives me 71% to 77% for the actual true population proportion should fall. And we could say from 71% to 77% of all Americans support Obama. Now this is inferred from our sample, which was the poll. Let's move to the next one. Let's say a poll asked all 400 high school students in one high school, who of them own a smartphone? Let's say 300 of them say yes, so this is 75%. There's no need for us to find a margin of error because we asked all of the students. That is the population proportion. That's the actual answer. But we don't ask all of the population in every study. So we do samples. So let's say of our high school, we do a random sample of 25 students and 18 say yes. 18 out of 25 gives us about 72%. And let's just say we take another random sample. We could even have some of the same students in that sample because it's totally random. And out of that, we have 20, which is 80%. And another sample of 25, we just pick these names out of a hat, and we get, oops, that's wrong. That should be 16, which is 64%, and so on and so on. And if we keep doing random samples of these 25 students in each sample, most of the time we'll get a percentage around the 75% because we know that the actual proportion is 75%. The further away we get from our 75%, this should be 75, our 75% get increasingly rare, which, if you think about all of these sample distributions coming down, it looks like a normal distribution, which leads us to the central limit theorem. The central limit theorem states that the distribution, and distribution means like the shape, from many, many samples, all of the same size, just like we did with the high school students, each of our samples was 25 students each, is approximately a normal distribution. And the mean of all of these samples, or mu, is equal to the true population proportion of the entire population. Sampling distribution is the distribution of the proportions of many, many samples. Here we go. So, and the central limit theorem states that if the more of them we gather of these 25 different samples, it'll start looking like a normal curve. One way of demonstrating this is kind of fun. I have this sampling distribution here. So right here in the middle would be our 75% from our high school. Now what we're going to show is right here the sample data. So this would be my 25 students. However, ours is only going to do 10. So I animate. That means that I gather 10 data points, and each of these students falls somewhere here. And the mean of all of that data is 14.29. So I know this isn't the exact situation. It's just showing us kind of what the difference between the sampling distribution versus just the normal bell curve. So here are all of my data points. So it would be like our high school example, except that there was only 10 here. And then the mean of those falls right here. All right, let's do another 10. So we do another group of 10. Well, there's where the mean falls. So I add another here. Remember, these histograms are like a frequency chart. And so I'm making this another size higher. Let's animate it again and show another 10. Okay, so this one's not in the exact spot. It's a little different. And we should expect that. A couple of them will find themselves a little out. So here we go, another and another. Do you see how all of these data points are creating another data point on another graph? Because these are my samples, and this is what I got from that sample, creating my sample distribution. This is my sampling distribution. Now the central limit theorem says the more and more and more of these I do, the more it will end up looking like a normal curve, which we're getting close. Now I can keep doing this 10 at a time, or I can click this and do 1,000. There we go. So it just sped things up, and I didn't have to push that 1,000 times, or I could even do 10,000. Takes a minute, but are you seeing the more and more I do, the more it looks like a normal bell curve? And each of these data points here represents a sample of, in this case, 10. In our case, on the other page, it was 25. So in this sample distribution, this was each and every single student being sampled. Here is one sampling of 25, or if this one, it would be 10. And so the central limit theorem says the more and more of those I do, the distribution of many samples of the same size, it ends up being approximately a normal distribution where the mean is the true population proportion for the entire population. The sampling distribution just says that I'm taking the samples from the population, different random samples, and they all have to be the same. And what does it end up looking like? And the central limit theorem says that the more of them I'm doing, the closer and the more normal my curve ends up looking. Now remember, we had a rule from our last section. It was the 68, 95, 99.7 rule. Remember the 95% rule, or the 95? The 95 said that within 2 standard deviations, 95% of the data falls. That's pretty significant. Yeah, not statistically significant, but it's significant. And in our last section, we were just given the standard deviation, and we added and subtracted. In this case, I think this was the quarter example. Now we're actually going to calculate standard deviation in our sampling distribution, where our standard deviation equals 1 over 2 square roots of n, n standing for the sample size. So if we were to do our example of the high school students, n would be 25, and we would have the standard deviation 1 over 2 times the square root of 25 gives us the sample distribution of 0.1. So the mean ended up being, and we happened to know that the mean on our high school students was 75%, and then we just add our 0.1 and subtract our 0.1. Oh, never mind. This is from our high school example. It was 75%, so we add 0.1 from 75% to 85%, add another 0.1, gives me 95%, and then we subtract to go in the other direction. But remember, we were looking at the 95%. That's 2 standard deviations. So we take our standard deviation, and because we want 2 of them, we multiply both sides by 2, and within 2 standard deviations, we get 1 over the square root of n. And since 95% of the information is between 2 of those, if we were to add 2 standard deviations and subtract 2 standard deviations, we would have 95%, and we would be 95% confident that the real mean, now remember, because we aren't absolutely positively sure because we didn't do a census. However, in our case, to show where we came from, on the high school one, we did find it. But in all of our other ones, we aren't going to pull all of the Americans. So if we add 2 standard deviations and subtract 2 standard deviations to the mean of our sampling distribution, we will have 95% of all the data, and therefore we're 95% confident that the real mean is somewhere within here. Because the further away from the mean of our sampling distribution ends up being further and further and less likely. Increasingly rare, as we talked about earlier. Which moves us to confidence intervals. A confidence interval is your mean, adding and subtracting our margin of error, and I always abbreviate it MOE or MO, and that's 2 standard deviations, which is 1 over the square root of n. Remember, we talked about it up here. That's how you're going to calculate it. By the way, that's not provided on the statistical formula sheet on the test. You will need to remember it's 1 over the square root of n. And we add and subtract that to our sample result, and therefore we can state that we're 95% confident that the true population proportion is within this interval, because 95% of the data falls within 2 standard deviations. Also, please note that the margin of error will decrease as the sample size increases. So if you want to have a smaller margin of error, you increase your sample size, and vice versa. All right, here is my hard and fast rule for margin of error. I'm going to highlight that for you too. Remember, this is not given to you. You need to remember the margin of error for a confidence interval, because we want to be 95% sure, is 2 standard deviations, and that came from our 68, 95, 99.7 rule. And this is standard deviations from our mean from here, which was our sampling distribution. Lots of different samples. All right, let's move to the next one. A poll finds we have a couple of polls we want to talk about, and we want to find the 95% confidence interval for these polls. So the first poll, we only poll 500 people, and 54% of them are voting for some county tax increase, whatever it be for. And we would like to find the margin of error and the confidence interval. Okay, margin of error, we just highlighted it. It's 1 over square root of n. N standing for, do you remember? The sample size. And we polled 500 people. 1 over the square root of 500. Calculating that in your calculator is 0.045. Okay, well, so far we have margin of error. That's nice. But we need the confidence interval. From what number to what number? They gave us our mu already. It was 54%. So we take our margin of error, our little bit of wiggle room, we add and subtract it to our 54. So 54%, add and subtract, change this to a percent, is 4.5, gives us 49.5 to 58.5. And we like to write it in interval notation, which is parenthesis, low number, comma, upper number, close parenthesis. That's called interval notation, and it's read, 49.5% to 58.5%. Please don't switch those numbers, because we're moving from a low number to a high number, just like counting. Okay, let's take our second poll. 1,500 people. 85% of them state that they're in favor of some certain bond. So we need to find the margin of error, which is 1 over square root of the sample size, in this case 1,500. So we do 1 over square root of 1,500. Notice the margin of error is smaller. We stated that earlier too. The margin of error will decrease when the sample size increases. So this one has a smaller margin of error because we can be a little bit more confident with it since we polled more people. We're getting closer to the population, right? So now we take our mu, which was 87, or our statistic that we are given, and add and subtract our little margin of error. So 87 plus and minus the 2.6 gives me my wiggle room from 84% to 89.6%, or writing it in interval notation. All right, let's get a little bit more away from it, a little bit more complicated, I guess. Not complicated, a little harder. We're taking some of the scaffolding away. 2,160 unemployed in a sample of 60,000. We want to find the margin of error and the confidence interval with this statistic. We polled all 60,000 and we got 2,160 were unemployed, and we want to make an inference about the true entire population proportion. So our margin of error, remember, 1 over square root of n. You remember that now. N standing for sample size. Our sample size was sample of 60,000 people. So 1 over 60,000, an even smaller margin of error of 0.004. Now normally we would just add and subtract it to the percent given us, but we weren't given a percent. We were told 2,160 employees were unemployed out of the 60,000. So we need to find that percent by dividing 2,160 by 60,000. So dividing those gives me 0.036 or 3.6%. Change this to a percent by moving the decimal over twice, gives us 0.4%. Add and subtract it to our statistic that we were given, and we get 3.2% to 4%. And we can state that we are 95% confident that the true unemployment rate for whatever our population is lies between 3.2 and 4%. Do you remember why we can be 95% sure, confident? Because 95% of the data falls within those two standard deviations, which is where the confidence interval came from. Let's move to Roman numeral 3, hypothesis testing. There's a lot of information in this section, so that's one reason you need to read through it before you listen to the video lecture. Let's suppose there's a company called Gender Choice that can increase the chance of giving birth to a girl up to 80%. Now we know that the chance of getting a girl is 50 out of 50. So their claim is that the chance of having a girl is greater than 50%. A random sample of 100 babies, if we take this random sample, if gender choice does not work, then we should expect about half of them to be girls, or 50%. If it does work, we should expect more than half of the babies will be girls, or more than 50%. Let's move into the two hypotheses that we need to discuss. There's the null hypothesis and the alternative. The null hypothesis in this case is that gender choice does not work and the proportion of girls equals exactly 50%. The alternative hypothesis is that gender choice works and the proportion of girls is greater than 50% out of some random sample of 100 babies, right? And a couple of definitions. The null hypothesis is where the population parameter equals the claimed value. The alternative is that the claim that is accepted if the null is rejected. So it's kind of like the opposite. I like to keep these separate by thinking of the null, the two L's on the null, tipped over, and it gives you the equal sign. So it has like a little reminder for you in there. The alternative will always have a greater or lesser than sign. So I guess if you tip over your capital A, you get kind of a, whichever direction you tip it, you get kind of a lesser than or equal than sign. And that's how I remember between the two. So if you're trying to figure out which one's which, see which claim has the equal sign, and then you can do the alternative with the greater or lesser than. So let's take our first example. We're going to practice finding the null and the alternative. So let's say a car company advertises that this particular car has a fuel economy that averages 38 miles per gallon. Okay, so it's averaging exactly 38 miles per gallon, right? Well, there's our null hypothesis, that the average mile per gallon equals 38 miles per gallon. The alternative is going to have a greater than or lesser than sign. Well, this car company is not going to have greater than that. So the alternative will be that the miles per gallon is actually less than what they're claiming. So that's the alternative, that the average miles per gallon is less than 38 miles per gallon. A couple of options for our hypothesis testing. We can reject the null. You can toss it out and reject it when there's no evidence to support the alternative. Or we can fail to reject the null when there's lack of evidence to support the alternative. You cannot accept the null. I'm going to highlight that. You cannot accept the null. It's kind of like a innocent until proven guilty kind of a thing. You cannot accept the null. You can only fail to reject it because there is a lack of evidence supporting the alternative. All right, let's move on to the outcomes of testing the hypothesis testing with gender choice. So if we reject the null, oh, I shouldn't have scrolled down. Let's go back. The null hypothesis claims that gender choice works and the proportion of girls does not work, and the proportion of girls equals 50%. So if we reject the null, that means that there is some evidence supporting the alternative. And we can go ahead and accept the alternative. Remember, you can't accept the null, but you can accept the alternative that the percent of girls is greater than 50%, that there is support behind their claim. Now, what if I fail to reject the null? That means that there's no evidence to doubt the null. It doesn't prove that the null is, it doesn't prove it. It just shows that there's a lack of evidence to show that gender choice works, but it doesn't prove that it doesn't work. That kind of gets double negative in there. Okay, hypothesis, test, decision. How do you decide which one you're going to use? If you're going to accept or reject or fail to reject? If a sample result is less than 1 in 100 or 0.01, the test is significant at the 0.01 level, there is strong evidence to reject the null and therefore accept the alternative. If by chance the sample result is less than 1 in 20, the significance is at a level 0.05 level, there's moderate evidence to reject the null. If it is greater than 1 in 20, then there isn't sufficient evidence to reject the null. You cannot accept the null. This is where you would fail to reject. Fail to reject the null. All right, let's put that into play with an example. A county health official believes the weight of male babies at their local hospital is greater than the national average, which is 3.39 kilograms. So they take a sample of 145 male babies, and they find that they have a mean of 3.61 kilograms. I'm going to kind of highlight that just for our going back to and the national average of 3.39, just so we can remember where those numbers are. All right, and it shows a probability of getting a mean weight of this particular 3.61, and you don't have to calculate it, it's just given to you, is 0.032. All right, so now we have the significance level. Find the null and the alternative hypothesis, and then determine what our result should be. Should we reject or fail to reject? Okay, so remember the null has an equal sign. What is the statement here? The county official believes the weight of the male babies is greater than. There's our alternative. So we can say the male babies is greater than the national average, 3.39. So in that case, I'm going to do the alternative first, that male babies at this hospital is greater than 3.39 kilograms, which gives us the null hypothesis that male babies at this particular hospital weigh the national average equaling 3.39. There we go, up here. Now we were given 0.032 as our after the calculations. This falls here. It is less than 0.05. It's greater than the 0.01, so it can't be in this category. It is less than 0.05, which gives us moderate evidence to reject the null, which means we have moderate evidence to reject this hypothesis and tentatively accept the alternative that male babies at this particular county hospital does weigh a little larger than the national average. But we can only tentatively say that because it's only a moderate evidence. All right, good luck with section D and hope to see you for the next section.